Hello, everyone, and welcome to our next lesson in Unit 9 on equilibrium systems, where the more things change, the more they stay the same. And that might sound kind of like a mouthful, but hopefully by the end of this, it should make a little bit more sense. So we'll talk about equilibrium systems, what they're all about, what they mean, how we define them. We'll look at a few different examples of different types of reactions that can obtain an equilibrium. So by the end of this lesson, you should be able to explain that some chemical and physical changes can reach equilibrium. And you should be able to explain that at an equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And that statement in itself is kind of the basis of what equilibrium is all about. So equilibrium, what is it? It is a state of rate balance between two opposing changes. And the key here is underlined. It's a rate balance, a balance of rates between two different changes. So it can be achieved in a system when a reaction goes forward and backwards at the same rate at the very same time. Put in simpler terms, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. And we'll look at a few different examples here. But not all reactions are going to achieve or reach equilibrium. We'll consider a general reaction between reactants A and B to yield C and D plus energy. This would be a forward reaction, and this would be considered exothermic because energy is being written as a product. The reverse reaction, now some of you had questions on this, of how to actually write these. We basically take the forward reaction and we start where our products are and we end where our reactants are. And we just write it in the reverse direction. So C and D and energy become our reactants, A and B become our products, and that is what we call our reverse reaction. Now an equilibrium reaction is going to look similar to the forward and the reverse, but we're going to see a main difference there. And that difference is this double arrow. I've had some questions on this throughout the year. And what that double arrow means is that this reaction can go forwards and backwards, and it's going to be able to achieve equilibrium, or it can achieve equilibrium. So what it's trying to tell us here is that this reaction, both the forward and the reverse, are happening at the same time. And when the rate of formation of C and D equals the rate of formation of A and B, considering both forward and reverse reactions, this reaction will achieve equilibrium. And I'll show you an example of this with the simulator momentarily. Now, an actual example here, we have a exothermic reaction, again, because heat's written as a product. This is a what type of reaction? Give you a second to think about this. It is a synthesis reaction in the forward direction. We see that with the forward arrow. So it's a synthesis reaction. We know the opposite of a synthesis reaction is a decomposition reaction, which is where we take the compound ammonia and break it down back into its elements. This reverse reaction is now endothermic. The heat value is listed on the reactant side. And we're taking the compound and breaking it down into elements, which is the reverse reaction of a synthesis reaction. Now, once we include the double arrow, this is saying that, well, we can form ammonia from its elements at the same rate that we can form its elements from ammonia. And that's what we call an equilibrium reaction. They look very similar, but the equilibrium reaction is going to have that double arrow there. So that's going to indicate to us that this reaction can achieve equilibrium. So you can kind of think of it as if you're going up a down escalator. The escalator here is coming down, and you are trying to walk up the escalator. If you take a step at the same rate that the escalator is moving downwards, you're going to be moving. You're going to be moving your legs, and you're going to be stepping up steps. The escalator is going to be moving. It's going to be moving downwards. But to somebody looking at this scenario, it's going to look like you're kind of just staying in the same spot. because you've matched the rate going up with your step as the rate of the escalator going down. And the key here is that it's the rate. So you essentially wouldn't be moving anywhere. You'd be stuck in the same spot in space as long as your rate of moving up the stairs matches the rate of the escalator coming down. Now, if you wanted to actually walk up the down escalator, you'd have to have a forward reaction or moving up the escalator that's greater than the rate that the escalator is coming down. Now, equilibrium is what we call dynamic, meaning that it's in motion constantly, where molecules of reactant are reacting to form products at the exact same rate that products are reacting to form molecules of reactant. And just like on the escalator, the system is in constant motion, but it appears to be at a standstill. Now, a couple key points. Equilibrium can only occur in a closed system. If it's open, if we have a reaction happening in an open beaker, we have a reaction going on in here, particles are free to leave and enter. And therefore, we can't have equal rates of forward and reverse reactions because we have parts of our reactants or products that could be leaving and other things that could be coming in and disrupting that reaction. So it has to be closed. We'd have to put a lid on top here in order to make this or allow this reaction to achieve equilibrium. So nothing gets in, nothing gets out. It has to be sealed from the environment. If we are forming product and it's escaping our container, it can't react in the reverse direction to form our reactant, and therefore we can't have equilibrium. Now, as long as we keep the system closed, a system that is at equilibrium will remain that way forever. Changing any of the conditions of the equilibrium will change the equilibrium. And we'll talk about that later. But that's what we call the Chatelier's principle. That'll be our last topic of this unit. Now, equilibrium can occur at different concentrations. The concentrations don't have to be the same. So we can have different concentrations of reactants and products. Now, changing concentrations of those reactants and products can change when we get to equilibrium, but it's still always reached as long as the rates of the forward and reverse reaction are the same. I'm going to show you a little bit about this before we continue on to our next section here. Now, we have a simple reaction here, and you can see we have a potential energy diagram that's separating our reactants on the left and products on the right. And right now we have equal amounts of reactants and products, 10 green and 10 red. On the top of this container, we see a double arrow, A forming B and B forming A. So the forward reaction is A forming B, and the reverse is B forming A. Now, as far as collision theory is concerned, all this simulator is showing us is the energy needed to form reactants or products. So on the left side here, these reactants have an initial potential energy around 15. There's no unit here. And the products over here have an initial potential energy of maybe around 8. So there's a lot more potential over on the reactant side, and therefore these reactants need a little less energy to get over this hump here and get down here to form product. But on the reverse, if we look at the reverse reaction from B to A, these red dots need a lot more energy from 8 up to 25, difference of 17, whereas these ones need a difference of 10. So 7 more energy units are required from the right side to get over the hump here to form our product. Now, right now, no reactant is forming any product and no product is forming any reactant. Our temperature is relatively low, and you can see this constantly fluctuating as these reactants and products gain and lose energy. Now, if we wanted to give them more energy, well, they're going to be moving faster. They might collide with each other. Oh, and there goes one. we now have, well, it's 10 and 10 still. So let's give this some heat here. These are going to start moving faster. And if they're moving faster, they're more likely to have enough energy to get over that hump. Now, as one of our reactants forms products, we can see we now have less here, 9 compared to 11 over on the left here. And we should generally see this number start to go down because less energy is needed to form product B over here. And we start to see that. This has gone down from 10, and this has gone up from 10. Now this will continue. This is constant. This is a closed container, so we can achieve equilibrium here. And every time a red one forms a green one and a green one forms a red one, we can consider that equilibrium as long as their rates are the same. Rate being 1 green per second, let's say, and 1 red per second forming a green. If those forward and backward reactions are happening at the same rate, 1 and 1, 1 and 1, we have what we call equilibrium. Now, right now, these numbers are hanging around 8 and 12. And this isn't the concern here. The numbers can be different. This is different concentrations, and that's fine. But every time this number goes up, we see a corresponding drop here and vice versa. But the key to achieve equilibrium is the rates. So not the amounts, but the rates at which these are changing. And right now, I would not call this at equilibrium. This one continues. The forward reaction is more aggressive than the reverse reaction. Now this reaction can achieve equilibrium. It seems like we might need maybe a little less energy or maybe a little bit more energy. If these guys aren't having enough to get over here, but if we do this, if we give this more energy, not only are these guys going to have more for the reverse reaction, but the green ones over here are going to have more energy for the forward reaction. We can kind of look and monitor some of our numbers here and see what's happening. Now, one of the things that I'll liken this to, and we'll talk about this in the PowerPoint in a second, think of this container as a closed bottle of water. You might notice this if you leave a bottle of water on your car sometimes. You get some condensation that'll form up on the upper part of the bottle. And let's call this liquid water and gaseous water. Inside your bottle of water, you're going to have liquid that's going to evaporate and turn into a gas. That's what we, well, we don't see it. We'll see it eventually as condensation, but that's liquid that's being evaporated and then condensing onto the bottle itself. So we have liquid water that's evaporating, but then that evaporated gaseous water vapor is condensing back into a liquid. And if one water molecule becomes a gas and one water molecule becomes a liquid, and it's a 1-to-1 exchange or an equal rate, then we have an equilibrium, as long as we keep the cap on top of the bottle. And we'll talk about exactly what that is. Now, given these more energy, our numbers have kind of balanced out here, but this one has gone way up, and this actually seems to be going down more. So these guys with more energy, it looks like the reverse reaction here has been much more aggressive than the forward. These numbers are starting to settle out around 10, and we kind of see a 1-in-1 adjustment at this point. And that was achieved by increasing the temperature for this particular reaction. So we're going to look at 3 different types of equilibrium: chemical equilibrium, solution equilibrium, and physical equilibrium. And all of these types of equilibrium will occur when rates of change are equal. So the first example here we'll look at is chemical equilibrium. And just like any equilibrium, this occurs when the rate of the forward reaction is equal to the rate of the reverse reaction, or the rate at which ammonia is being formed equals the rate at which ammonia is being decomposed. We've talked about the Haber process before, the basis of a multi-million-dollar cleaning industry. And when the synthesis reaction equals the decomposition reaction, then we achieve equilibrium. Synthesis being the formation of NH3, and decomposition being the formation of N2 and H2 from the ammonia. The other type is solution equilibrium. This occurs when our two changes here, dissolving and precipitating, those are the two opposing reactions, dissolving and precipitating. But solution equilibrium occurs when we have a saturated solution where the rate of dissolving equals the rate of precipitating. So if we tried to dissolve sodium chloride, solid sodium chloride, into water, sodium chloride is pretty soluble in water, but at some point we're not going to be able to dissolve anymore. And we get a saturated solution when we start to see in our container here some solids start to build up on the bottom. So as we're adding more, it's going to dissolve. But when we start to see it on the bottom here, this is precipitate. That's our solid. That's going to mean saturated. We'll learn about that next unit in detail. So when we put the sodium chloride in, it dissolves. As the concentration of dissolved ions in the water increases, again, those sodium and chloride ions are going to run into each other. And with the right orientation and energy, they can recombine and form sodium chloride solid, or what we call a precipitate. When we can't put any more salt into the solution without the precipitate or more solid being formed on the bottom, we say it's saturated. When the rate of dissolving equals the rate of precipitating, or the forward equals the reverse, then we have what we call equilibrium. The solution equilibrium is what we just looked at with the simulator, talking about the bottle of water. Oh, not yet. Oh, this is another example here. If we put our salt cube in a beaker of saturated sodium chloride solution, the cube's going to change shape over time. We put a square cube in here. This cube is going to change shape over time. It might look kind of like something like that. As some of this salt cube dissolves back into the solution, and some of the solution dissolves or precipitates back onto the solid itself. So it's going to change shape over time as long as this solution is at equilibrium. Well, physical equilibrium or phase equilibrium is what we talked about with the simulator. So we have a closed container here, and we have some liquid, and we have some gas. So the two opposing changes here are evaporation and condensation in this particular case. It could be freezing and melting. But it's only going to occur at the phase change temperature. It's the only time we can have equilibrium. So if we're talking about water, it's got to be 0 or at 100 degrees Celsius. So in our simulator example, we're talking about the boiling point of water, essentially, where we have some water that's being evaporated into a gas, and some of that gas being condensed back into a liquid. That's only going to occur if we keep the system closed. Same idea at 0 Celsius. The rate at which ice molecules melt has to be the same at which the rate of liquid water is freezing, or the rate at which liquid molecules are freezing. If we increase the temperature above 0 Celsius, a few degrees let's say, more molecules are going to melt than would freeze, and we're not going to be able to achieve equilibrium there. At this point, you should be able to explain that some chemical and physical changes can reach equilibrium, and that at equilibrium, the rate of forward reaction and reverse reaction rates are going to be the same. Make sure you guys write down any questions that you have. Make sure you ask them when you see me. Have a great day.